In this video, I will be explaining how we use chi-square to carry out tests of independence. From a previous video, I already taught how we can use chi-square to carry out tests concerning more than two population proportion. There also I explained how we can use the beta epsilon chi-square factor algorithm to obtain chi-square calculated instead of going through full tabulation, a usual general format. So here we're going to learn how we can use this same chi-square to now carry out test of independence, no longer test of homogeneity that we've done previously. Please, you can search through our YouTube channel here in order to watch the video where I explain how we can use chi-square to carry out tests of homogeneity, tests concerning more than two population proportion. For now, let us focus on how we can test for independence. We have a question here we are going to use. So let's read the question together. It is surveyed to study the relationship between COVID-19 infection and wearing of nose mask. The following data were obtained. So these were the data obtained. This is the state of health of people, those infected, those not infected, based on whether they do not use nose mask at all, so have non-users, or whether they are irregular users, they use but not always, or whether they are regular users. So these were the data obtained. Please, before I move on, let me quickly say this. These data were not generated from any field survey. I generated them. Our interest is just to see how we analyze these data and use chi-square to test and know something about whether we can accept the claim or not. Alright, so at the end of whatever we are going to get when I'm done with this, I may likely make a disclaimer depending on what we get at the end. Until then, just follow along. The question requires that we test whether COVID-19 infection is independent of nose mask. Now they gave us 1 minus alpha, which is equal to 95%. This 1 minus alpha equal to 95%. You see, this 95% is a value higher than 50%. Alright, it is higher than 0.5 in decimal, 50% in percentage. Simply tells us that this is confidence coefficient. I made reference to something like this when I taught tests of homogeneity, alright, tests concerning more than two population proportion. So once you're given 1 minus alpha, please take note, that is not significance level. Rather, it is confidence coefficient. So if your chi-square table is constructed in that confidence coefficient, fine. You use it straight ahead to read. But if your table is constructed in significance level like mine, I'm going to show you, then you would have to convert this to significance level by determining the value of alpha. And that is what I'm going to do because my table is actually constructed in significance level. So let us look at this. 1 minus alpha is 95%. 95% is 0.95. So I will now get my alpha by making alpha subject to the formula. If you do that, it will be 1 minus 0.95. And that will give us 0.05. That 0.05 in decimal can still be converted to percentage, is equal to 5%. Because 0.05 times 100 will give you 5%. My table actually is in percentage, significance level, percentage. So that 5% is the same as the 0.05 which we got for our significance level here. Alright, let us quickly check for the degree of freedom because it's another critical value for us to get to know so that we can be able to get chi-square tabulated. The degree of freedom when carrying out tests of independence is equal to number of rows minus 1 times number of columns minus 1. Take note of that. Taking our mind back to what I explained when we treated test of homogeneity, the degree of freedom there is simply number of column minus 1. But in this case, you see, you take note of number of rows minus 1, again, number of columns minus 1, then you multiply them. Therefore, for this our table, the number of rows which I use R to represent is 2 rows. So it's going to be 2 minus 1. Number of columns is 3 columns. You can say that. C here represents number of columns. So minus 1, you're going to have 2 minus 1 and then 3 minus 1. Multiply them, you get 1 times 2, which is equal to 2. So the degree of freedom we are going to use in checking this significance level of 0.05 or 5%, that degree of freedom is 2. So you take a look. I've actually highlighted what we need. Alright? So if you look at this, you will see clearly that degree of freedom 2, you can say that, corresponding to the significance level 5%. This 5% is 0.05 if you divide it by 100. When you trace the 5% column, downward, and you trace the degree of freedom 2 horizontally, both of them will intercept at a value that I highlighted there, 5.991. That 5.991 is our chi-square tabulated at this significance level of 0.05 and degree of freedom 2. And of course, that is how I got this chi-square tabulated to be 5.991. Now we can state our hypothesis, the null hypothesis and the alternative hypothesis. Of course, it's your choice. You may choose to state the hypothesis first before getting the chi-square tabulated. That is completely your choice, alright? Now, what is going to be our hypothesis? Remember, we are carrying out test of independence. So the null hypothesis will say that yes, COVID-19 infection is independent of wearing of nose mask. That is what the null hypothesis would be. It always go in line with what you're trying to test, because we are actually testing for independency. Alright? Then the alternative hypothesis will always be against the null hypothesis. I said that in previous videos already. So the alternative hypothesis will be telling us that COVID-19 infection is dependent on wearing of nose mask. No, we just can't accept any one of the hypotheses just like that without testing them. So what do? We need chi-square calculated. Once we get chi-square calculated, we compare it with the chi-square tabulated, then come up with our rule, which I already explained in our previous videos. Please do well to search through Jimas41's YouTube channel, check for the video and watch. Is that okay? Now we'll take a short break. When I'm back, we shall use the beta epsilon chi-square factor algorithm to quickly obtain chi-square calculated and do our comparison. You're welcome from the short break. Before the break, we obtained the value of chi-square tabulated at significance level of 0.05 and degree of freedom 2 to be equal to 5.991. We now wish to determine the value of chi-square calculated. Alright? To get chi-square calculated, we use the beta epsilon chi-square factor method. Remember, by the general method, one can still choose to do your full tabulation and then you use it to solve for chi-square calculated. But I prefer going by this formula. It's faster for us to get chi-square calculated. Is that okay? Without constructing much tables. Now what do? How did we get this? How did we arrive at this chi-square calculated to be 4.469? And then with this decision we made here, where I wrote conclusion. To quickly do that, you take note that our table has taken another form. There are some added numbers there. Okay? 80, 55, 65, 150, 50, and 200 are added values. What do they represent? This 80 is column total for column 1. So let me write CT1. This one column total for column 2. This one column total for column 3. And then this 200 is grand total. If you add up this vertical column, you get this 200, or you add up these terms in the horizontal row, you get this 200. It's still the same as adding all the observed values, observed frequency you obtained from the table given in the question, okay? Alright, now having said that, if you look at this formula, what are the things we need? Our observed frequency for a particular row, nth column, we have the values there, 55, 40, 55, 25, 15, and 10. the data that were generated. Are you following, right? So we know the observed frequency. But our expected value is the problem. The expected value for each of these items is obtained from this part of the formula. Ct sub n times beta. Beta is chi-square factor for rho 1. And then epsilon here, chi-square factor for rho 2. You could see it in the formula rho 2, rho 1. Is that okay? So this part of the formula, this part, or even simply this denominator, that is what you use in getting your expected frequency or value. Because each of these observed frequency produces its own expected value, what you expect of it. Even if these were the data you obtained, you got from the response. Each of them still have what we expect of them, refer to it as expected frequency or theoretical frequency or value. So, like I said, to get each of the expected frequency, this part of the formula gives them to us. This for rho 1, this for expected frequency of each of rho 2 data. Alright, we need the value of beta and epsilon. We've gotten our column total for each column. Look at them. So how do we get our chi-square factor for rho 1, beta? Say, but beta is equal to, since it is rho 1, you go to rho total of rho 1, which is 150, divided by grand total, 200. If you do that, 150 divided by 200 will give us 0.075. Okay? Now, let me show you something else. We can get our epsilon. Epsilon will be, remember it is chi-square factor for rho 2. So you sum everything in rho 2, which gives us 50. And then we divide it by grand total, 200. If you do this, we are going to get 0.25. It is important for me to state that if it is just 2 rows, I repeat, if it is just 2 row contingency table you are working with, like this is just 2 rows. Once you know the chi-square factor for one of the row, the chi-square factor for the second row is simply 1 minus the chi-square factor of the first row. If I didn't want to do row total of rho 2, which is 50 divided by 200 to get 0.25, I could have simply done 1 minus 0.75 to get this 0.25. Very important. As a matter of fact, I want to state that this Omeka's beta epsilon chi-square factor method has an alternative formula of it, where this epsilon, which is rho 2 chi-square factor, is not even necessary. We can write this part of the formula in terms of rho 1 chi-square factor. Alright? So you go through our YouTube channel, search for the video, you're going to encounter that. Watch it out and you will learn something great. Now that we've obtained our chi-square factor for both rows, all we need to do is to come here and substitute this one summing over rho 1. Are you getting? So we have observed frequency rho 1 column 1, rho 1 column 1, that is 55. You substitute 55 minus open bracket column total of the nth column you're dealing with, that is of the column of 55. The column total is 80. You fix it up times 0.75. The 0.75 is chi-square factor for rho 1. We got the value already. And close in bracket and then square everything you have in the numerator, divided by the denominator is always these parts. Column total of the nth column times the chi-square factor of the row you are dealing with. So look at it. Do same, it will be plus. You move on to observed frequency of rho 1 column 2 this time around. You also do for observed frequency rho 1 column 3. For that of rho 1 column 2, it will give you 40. Rho 1 column 2, 40. So you fix up 40 minus open bracket column total of that nth column you're dealing with now, which is that of 40. The column total is 55. So times 0.75 and close everything in bracket in the numerator squared divided by this part of the formula. You do same as well for rho 2, you know. You can check through now for this one in rho 1 column 3, that of 55. Let's quickly check the value of rho 2 column 3, which is that of this 10. Okay, rho 2 column 3, that will take us to the last term here. How did I get that? You come to this part of the formula because here sums over rho 2. Rho 2. So you go, observed frequency of rho 2 column 3. Rho 2 column 3, that is 10. You fix up observed frequency minus open bracket column total of that row 2 column 3 element. Row 2 column 3 element is 10. Its column total, look at it, 65. So it's going to be 65 times the chi-square factor of that row. Chi-square factor epsilon of row 2 is 0.25. Look at that. Enclose all the numerator in brackets, square it, and then divided by this part of the formula, 65 times 0.25. If you press this with the calculator, you're going to get 4.469 as chi-square calculated. Alright? So that's that. What you now need to do is to compare the chi-square calculated with chi-square tabulated. You will observe something. 4.469 is chi-square calculated, 5.991 is chi-square tabulated. Very clear that chi-square calculated is less than chi-square tabulated. So you take note of this. I'm going to use blue marker to underline. Okay? So chi-square calculated is less than chi-square tabulated. So what does that mean? Go back to our hypothesis. It means we are going to accept the null hypothesis H0 and reject the alternative hypothesis H1. Then we do our conclusion. Remember, your conclusion will be based on the decision rule. When chi-square calculated is less than chi-square tabulated, you are to accept the null hypothesis and reject the alternative hypothesis, which is what I've done on the board here. Then, what do we know? According to the null hypothesis we are accepting, it states that COVID-19 infection is independent of nose mask. So that will be our conclusion, alright? However, like I said from the beginning of this video, the aim of this is not to discourage wearing of nose masks. Please, this is not data generated from the field. It's not a survey from people's response. It's just something I brought out so that I can use to show you how we use chi-square to carry out test of independence. Is that okay? Anyway, my interest is to know that I always have my nose mask with myself. It's important, not just for the case of COVID-19. We know about several airborne diseases. And of course, this can actually help us a little, alright? It can help us. So please, once again, the fact that our conclusion says that COVID-19 infection is independent of nose mask, I am not saying that you shouldn't use nose masks, please. I've proven that I always have mine with myself. Perhaps, let me put it on. What do you think? Like that, right? Okay, so that is that about using chi-square to carry out test of independence.